this short recap here. Stuff that in here. And this is in reference to that first problem. Remember, the dihedral group generated by a rotation and flip, such that R to the fifth, squared 1 and SRS are input. Great. And we wrote this as, we did this example before. Remember how we did that? And let me point out that this is one, two, three, four permutations. So this is an A5. In S, the flip was 2, 5, 3, 4. Again, two transpositions. This is A5 as well. So in this case, with reference to the first homework problem for next week, D5 is contained in A5. Okay. All right. Any questions on that? Yeah, I'm gonna formally talk about. I wanted you guys to work through this problem. To kind of familiarize yourself or refamiliarize yourself with the alternating groups, the symmetric groups, and I'm gonna give you some theorems, and we'll talk a little bit more formally about that a little bit later, not too much later actually. Okay, so let's kind of pick up where we were. Okay, so we were just beginning. Last time I gave some examples with cosets and what that's all about. So let me get to definition here. In this situation, we're going to let H be a subgroup of G and A, B, and G. We say that A is right, respectively left, congruent to B modulo H. Respectively left, congruent B modulo H. If AB inverse is in H. Or respectively, A inverse B. So, no. If G is abelian, then A is right congruent to G. If and only if A is left. Right? Because if it's right congruent, then AB inverse is an H. But then the inverse of this is BA inverse, right? Which is still an H. and turning that around because of the fact that she's billion gives you. Everybody okay with that? Okay. Sarah here. Let H be a separate G. Right, congruence modulo H is equivalence relation. Mod H is an equivalence relation. The equivalence class A, G, which you will know A, or the equivalence class that way, under right, for left, congruence mod H is AJ. Under left congruence. And C the size of these equivalence classes are also. Okay, so let's maybe you'll forgive me here if I only go through doing right because the left is pretty much the same. First, we need that right congruence equivalent is an equivalence relation on G, right? So number A minus A, let's see which way is to right, AA inverse so A is equivalent to A. Okay, so that's the first important step in an equivalence relation. A be equivalent to B. So this means that A be inverse is an H. Now I think I know what's coming, right? H is a subgroup, so it's closed under inverses, right? This is a subgroup G. So AB inverse, which is BA inverse. So B equivalent to A. I'm on a roll here. So 3, suppose A is equivalent to B, and B, actually at this point I should say related. I don't know if it's quite yet. So we have AB inverse and BC inverse for both in H. Because of this, but of course, groups are closed under multiplication, so AB inverse, BC inverse, AC inverse. So A, okay, so it's equivalent relation. What cool then? Equivalence classes. What are the equivalence classes under this relationship? Well, the equivalence class of A, this is just a set of X such that X will be A, H, which is the set of X and G such that which is the set of X and G such that X is oops. Let me just make sure that we're all good with this last step, because what it means to be here is X is equal to HA for some H in here, correct? Which means that XA inverse in H includes inverse. Yes.
Is there an HA inverse? Like the other way around?
What's it now? Is there?
Like X is an HA inverse, is that a thing?
Oh, yeah, because A inverse is just another element, right? And so HA inverse, I mean, it's even possible that HA inverse and HA are the same thing, because this is a whole coset. So this is just a collection. This is a lot of laughs, because it's every hot that you can make running through all of H. All right, so it's just a set of things. Right, okay. Oh, right, the last one. HA equals H. C, claim. I want to make that claim here, and the other bit is the proof is the same, that it's equal to AH. The way I'm going to do this is I'm going to define a function F. This is like old-fashioned counting sets. I'm going to invent a function from H into HA, and it's going to take H. Now, note, X, okay. Let me point out that this function is clearly well defined, right? Your input is not ambiguous. In the H gives you an HA. So all we need to do is show that it's bijective. So if X is an HA, by definition, is the form this, which is F of H. So F is on to also F of H1 equals F of H2, then H1A equals H2A. And my next step is these things both lie in the group G, So I'm gonna multiply on the right by A inverse. So multiply both sides of this equation on the right by A inverse. And I get that. So F is 1, 1. So the size of those cosets H and HA are the same. And also AH as well. Okay, any questions? Corollary. Okay, again, same setup. We'll say that H is a set of G. A. Actually, I should write this out. Two right cosets. I don't thinking that I'm mixing and matching. If I compare two right cosets, or respectively two left cosets, I'm not comparing left and right. Cosets are either exactly the same or distinct. And this is actually very important because the cosets actually partition group G. By the way, what I mean by this dot here is this joint union. So when I union, so what I mean by this is if I accidentally get an A and a B and G that give you the same coset, because remember, they might be the same, then I'm going to throw one of them out. So I just take the distinct cosets. So G is the, for example, with many different elements, you might have the same coset, right? HA, well, I'm going to point out that the element A and the element HA will give you the same coset, right? And so I'm going to just throw up duplicates here. So it's a disjoint union of the cosets. For all A, B, and G, and the two right cosets are equal. If and only if B inverse, or I'm sorry, AB inverse is an H. And AH equals BH if and only if A inverse B is an H. And finally, number D. Where script R is number of distinct right cosets actually, let me change the notation. If R is the set of distinct right cosets set of distinct left cosets. Then this number is the same. Okay. All right, so let's discuss this here. Why is A true? There's a simple reason why it's true. You can actually do this by computation, but I prefer more simply. The cosets are equivalence classes. We might as well use what we've done. These are equivalence classes. So any two are the same. Doesn't have anything really to do with groups. This just has to do with equivalence relations. If you have an equivalence relation, it partitions the set. Y'all remember that from way back when. Equivalence relation partitions the set into disjoint equivalence classes. And conversely, if you have any partition, that gives you an equivalence relation. So really, that's all we need there. Number B. This also follows from the fact that this congruence modulates equivalence relationship, because here my underlying set is G, and it is partitioned into these cosets. Right? This is a partition, so the union has to be everything. Number C, HA equals HB if and only if AB is an H. A the inverse. I'll just do the first statement because the second is exactly the same with the letters turned around. So let's just do this statement here. Let's suppose first HA equals HB. So B is in HA. Let's see if I've done this efficiently or not. Therefore, there exists H and H such that B equals HA. And I didn't quite do this the way I wanted to, but no worries. Multiply this on the right by A, and I get B A inverse equals H and H. I think you can all agree with that. Therefore, AB inverse is H inverse. And there you go. On the other hand, in the other direction, suppose whichever AB inverse is an H. Therefore, so suppose that AB inverse is an H, you want to show that HA equals HB. So I guess what I want to do here is so I'm going to come backtrack a little bit before. Therefore, A is equal to HB. So A is in HB and A is in HA. A is in HB because of this computation here. A is in HA because all you have to do is take the element here to be the identity, and A is one of the elements. Right. For any coset, left or right, if you have HA, then A is automatically in there, and there will be other stuff as well. So HB intersect HA is not the empty set. So from the previous, right? Because those two cosets have something in common, so they have to be exactly the same. And I will leave D, I think I did sort of a function kind of proof in the notes. This actually also follows because D follows from this and the fact that the size of the cosets are the same, but you can look at D as well. That's another kind of approach. Okay, any questions? Okay, so questions? Let me give you kind of presentation. So these theorems are all going to help us count quite a bit. We know that the cosets, the left cosets, right cosets, they partition the group and they partition it into a disjoint set because the cosets are all disjoint. The distinct ones are. Definition. Subgroup, then notation E:8 is the number. And I put that in parentheses because it could be infinite. You can get more descriptive of that if you like. Distinct left, respectively right. Process. And so theorem, and then we'll use the next theorem to prove a very famous theorem by Lagrange. Theorem. Suppose we have a chain of subgroups. So I have K as a subgroup of H, which is in turn a subgroup of G. Then the index K and G, sometimes we use that terminology, the index. This is the number of, say, left cosets G and K. Multiplies. Yes.
1.4.
Mhm.
Say respectively, right? What is that was with respect to?
That means I could use the word left or right.
Okay,
Right,
so
so it's
there's
the
no,
number of
there's
left
no
cosets,
difference.
and the number of left cosets and the number of right cosets are the same, right? Okay, so, in like a beginning algebra course, oftentimes some of the beginning algebra books, they actually do some kind of counting to show this. I'm going to do this slightly more generally because this is even true if any of the numbers in there are infinite. So let's let H be the union of KBJ. Index set J. Where these denote the distinct cosets. So I'm gonna put a little dot over here. Just what union, so I'm gonna, so. And this will probably clear it up a little bit. The cardinality of the set J is this index here, HEK, because basically what you're doing is you're counting the number of cosets K and H, right? So this J is actually running through the disjoint. This is running through the disjoint cosets here. And similarly over here. Like that. Now, I claim, by the way, what we're trying to do here is we're trying to show in this formula that basically the cardinality of GK is the cardinality of this set times the cardinality of this set. Everybody agree with that? That's kind of where we're going with this. So, any ideas on a strategy? Right. So what I'm gonna, that's right. So I'm gonna claim the following. I'm going to claim, and this is really, once I do this, I've sort of broken the problem back. I claim that K, BJAI is a complete set of disjoint coset reps okay. Right, that's where I'm going with this. So basically what I'm doing is I'm taking all the different BJ and all the different AIs and I'm putting them together any really way I want. The number of indices that I can make here is the cardinality J times the cardinality of I. The burden is now to show that these things are actually all the cosets of K and G. This is where we're at. So the first thing we need this set of representatives to be complete. So let's note first that if you look at the union, and this is IJ. So if you look at this, this is actually KJ. What we want is we want this to be off G, right? So, but pick your favorite element of G. I've got to show that it lives in one of these things. Well, notice first that G G is HAI, right? Because after all, this is a complete list of coset representatives, G, so G lives in one of these things. And so I'll pick the appropriate H and the appropriate I, right? Now, let's pick apart H. Now, with this H here that appears here, well, H is in this joint union here. So for some choice of K and some appropriate BJ, it's in there. Right? Therefore, G is equal to H, I'm sorry, K BJ. H. So it's in one of these things. So this is all. Really what we've done is we've shown that G is contained in here, but clearly this is contained in G. It's a union of stuff that's in G. Now, what's the next part of our verb? So what I've shown is this big fat union of what I hope are cosets eats up the whole group, right? That's a good sign. But what do I need for my collection of these KBI, BJAIs? What do I need for these to actually be cosets? And make sure that I'm counting right. I need them to be distinct cosets, right? It occurs to me, what could go wrong is for some choice, J1, I1, it might be the, in J2, I2, it might be the case that K, BJ1, AI1 is the same thing as K, BJ2, F, AI2, right? So I've got to show this. So let's assume that assume K, BJ, AI is K, BJ prime, AI prime. So what that means is, in particular, BJ AI is K, BJ prime, AI prime for some K. Right, because BJAI is clearly here, so it has to be here. So there's some choice of K that makes this true. Right. Well, now recall that the B's and the K's are all elements of H, right? And so so what we'll get is HBJI is H K BJ prime. Or, so this is in H, and this product is in H. So I get HAI, HAI prime. So AI equals AI prime, because we assume that we pick different coset representatives, right? So that the AIs are all distinct. And now once we've got that, this equation now reduces to BJ equals K Bj prime. Therefore, I'm sorry. Right, I went the wrong direction. So therefore, KBJ equals KBJ prime, which implies and that should do it, because now that these cosets are distinct, we now have the index K and G, cardinality of I comes cardinality of J, which is G colon H. And like I said, this is true even for infinite sets. Let me give you a corollary. Any questions on the proof? Okay, so let me show you the power of this. Here's corollary. I really should call this a theorem because it's a very famous theorem, but I can't resist the fact that this just rips off what we have before. This is the famous theorem due to Lagrange. If H subgroup G, then the order of G is the order of the index of H and G times the order of H. In particular, G is finite. Finite, then the order of H is the order of G. And also, if A is in G, then the order of A divides the order of G. Because the order of A is the order of the subgroup generated by A. And so, by the previous remark. That's about it. So why do I call this corollary? Well, here's my short proof. Take the previous result, okay, the identity group. Then G colon the identity, G colon H, colon the identity, and this is the order of G. Remember, the index of the identity, how many cosets do you have when your subgroup's the identity? You have as many as there are. Okay, well, that's a dramatic way to finish off for today. Any questions on that? Okay, well, don't get your homework today. If you have any questions, I'll be in the office. I sent you all an email. I've got a meeting that I think will go very shortly at 11:15. But other than that, I'm available. I'm not y'all have a good weekend. Are you one of the ones that sent around that email about the reading?
Yeah.
You know, I wish I could, I am too busy to attend that, but I wanted to say that's a great thing you guys are doing. That's what graduate students should do. I think that's wonderful you guys are doing.
This is the first time we look at yeah, we will try to council. We will try several weeks and several times, and maybe we will adjust the kind of schedule, make the want some
office hours.
That's
right.
If they are.
It's from 2 to 4.
Three of us are almost new to this topic.
Right.
We want to do something in that area, so.
Well, I think it's great. Yes.
I applied the first discussion.
Yeah.
This opportunity.
It's based on my experience, so I need to talk some definition and concepts of what the
I'm a mathematical program.
Learn something and given lecture is totally different.
I felt so dumb.
Okay,
too,
you
don't
know.
worry. I was like,
Right.
I feel dumb. I'm like, feelings of validation by the fact that
On that stuff, or just move on.
my feelings are true because
Yeah.
Put a lot of
I am,
time.
right?
You guys will figure it out once you get going. Yeah, I mean, some things will move quickly, some things might take quite a while.
Friday.
Right, so am I gonna see you?
Yes.
Okay, sounds good.
Yeah, I don't know. So last time we need to write something on the whiteboard or blackboard on only 1 hour.
Right.
Yeah, my plan is okay. So just talk about some basic definitions only. And I don't write the basic definition, but I just talk a little about that definition, just some concepts and the theorem about the
Right.
probability theory.
Yeah, it sounds good. It sounds really good.
Yeah, I have already prepared for the notes, how to discuss it. It's 6 pages.
Oh,
So for 1 hour is not enough, to prepare it.
well, that's why you take a semester to do it. Yeah, it's difficult. Yeah.
Yeah, so
The first time I had a student that gave a talk, he said, oh, there's no way I can fill up this time. I said, you wait till you get up there and you will find that you will fill the time. Right, because you work on something for a while and it becomes familiar to you, and you forget that your audience is not familiar. Right?
yeah,
Yeah, you too. Oh, you might be interested in math. Because you were the one that asked me, right?
Oh, yes. Yeah. That comes to, so if you want to, so you first have to show that. So you have to calculate the time.
Yeah, I mean, that's one way to do it. Yeah, it's probably the best way to do it. But you have to know what is, you have to.
Yeah, I mean, it's so amazing, you can give an example of snapshot.
What's that?
I mean, it's so amazing, you can give an example of snapshot.
Oh, well, I know that stuff. It's kind of stuff that I did.
And I mean, for this, application, I mean, so you do it.
I think
Oh, you got it.
Yes, I think this is.
I'm just curious.
So let me see if I understand what you're saying. So you do something like this?
Here, the actual value is numbers.
Uncountable, countable, uncountable.
Okay. So, yeah.
Right.
So, and oh,
Yeah.
okay.
So the world is a nice place.